Hi, in this video, we're going to be looking at tutorial 5, question 1. Okay, so in this question 1, we are going to examine 3 instructions separately. Okay, and we're going to see how these instructions actually go through the pipeline processor, and we're trying to analyze the pipeline registers or latches that are used to store information as the instruction goes through from one stage to the next. Okay, so let's look at it at the first stage. The first stage is where you fetch this instruction from a memory. Okay, so when you fetch this instruction, of course, you are actually fetching a 32-bit value. And from this 32-bit value, to sort of derive this information that you see here is basically what we have done in previous tutorials, which is your MIPS encoding format. Okay, so as long as you understand the MIPS encoding format, from the 32-bit instruction, you can derive what is the opcode, the RS, RT, immediate, and so on. Okay. If you look back at our earlier tutorial 4 video, you will see that there are, for example, values for RD, okay, and values for function field. Okay. But because this is a load word instruction, we know that the RD bits are not being used and the function field is also not being used. Okay, so that is why we put X here. Okay, but if you look back at tutorial 4 video, there are actual values there. Only thing is that we are not using them here, so we have put an X here. Okay, so now before we look at the pipeline process, let's quickly recap the single cycle processor. So for the single cycle processor, if I were to just quickly go through, you can see that, okay, I'm going to be taking this 32-bit instruction, and once I get this 32-bit instruction, what do you see? You can see that automatically I will trigger the control unit, okay, and I will also get 15 here at RR1, 24 here as RR2, okay. But of course, in this case, it is this RR2 is not being used. In fact, this is going to be, okay, channel here, okay, because the register destination here is going to be a 0, okay, the RT bits here. And subsequently, I'm going to read from register 15, take the data from register 15. At the same time, I have an immediate value, 16-bit immediate value that I'm going to sign extend and pass it through this multiplexer. So the ALU source is going to be A1, and the ALU is going to do an add operation and give me the address, and from the memory, the data that comes through is what I want to channel back, okay, to my processor as the write data. Okay, and the register write will be a 1, mem to register will be a 1, and since we're doing a mem read will be a 1, mem write will be a 0. Okay, so I just have quickly gone through, okay, the whole flow from a single cycle perspective, and of course the more detailed explanation you can look back at the tutorial 4's video. Okay, so what is important here to note is all of these are actually available from the control unit over here. Okay, so the control unit is responsible for generating all these control signals. And if I look back at my pipeline processor now, basically once I pass my instruction to the decode stage, I'm passing this instruction to the control unit together with the register file and the sign extension. Okay, and I also am passing in through the RT. These are the RT bits location, and this is the RD bits location. Okay, so you can see that in the decode stage, I am basically going to take the information from the registers, as well as the control unit is going to generate all the control signals that I need. Okay, so as you can see, there are several, or basically 4 such pipeline registers or latches, and each of these latches hold different sets of information, okay, depending on the data that is coming in and the data that we are channeling to the next stage. Okay, and you can also see that the size of each of these latches would be actually different, okay, because it depends on the data it's holding. Okay, so just if you quickly look at just this latch here, IFID, you can see that it has 2 arrows coming in. Okay, one is this, which is actually your instruction, which is 32 bits, And you have this, which is PC plus 4. And PC plus 4 is also 32 bits. So your RFID latch is actually going to be 32 plus 32, which is 64 bits. Okay, so you need a total of 64 bits to store all the information in your RFID latch. Okay, but if you look at IDEX, for example, you need a lot more bits. Okay, you need RD1, which is already 32 bits, RD2, which is already 32 bits, this sign extension value, which is also 32 bits. Okay, then you have RT, RD, which are 5 bits, 5 bits, and your PC plus 4, which is another 32 bits, and all these control signals over here. Okay, so of course you can do a analysis on your own for all the different latches, and you can see the different latches have different size requirements. Okay, depending on the amount of information that I actually need to store in each of these latches. Okay, so coming back to our question, okay, once we fetch the instruction, okay, and we pass it to the decode stage, okay, we have the control unit which would have generated all these signals for us. Okay, this PC plus 4 is directly available from the earlier stage, and this R data 1 and R data 2 is actually available from the register file. Okay, and RT and RD are of course transferred from the earlier stage, and this immediate 32 is also available from the instruction directly. Okay, so this is what happens in the second stage, the IDEX stage. Okay, so the way to look at this, any of these lectures notation is, when I say IDEX, this ID is the information that I already obtained at the end of the decode stage, and this EX is the next stage. Okay, that means I'm going to pass all this information over to the EX stage. So what will happen in the EX stage? In the EX stage, of course, I'm going to do the ALU operation here. Okay, so in the EX stage, when I do the ALU operation, I would be using some of the control signals like ALU op and ALU source. Okay, and these control signals are only needed in this stage, and I don't need these signals anymore in the subsequent stages. Okay, so in a pipeline processor, some of these control signals will get carried forward all the way to the end. Some will be used in certain stages, and after that we won't carry on with them. Okay, so in the third stage, EX stage, I do the ALU operation. As you can see, I also do the addition to generate the branch target address. Okay, so this is a branch target address, and I also have the destination register here. So I would have made a decision on whether I need to write back to RT bits or RD bits, and I would have made a decision and channeled it here. And I also have things like your read data 2 over here, your is0, and so on. Okay, so all of this gets transferred over from the EX stage. Okay, and this is the information that I have at the end of the EX stage, which I will then transfer over to the MEM stage. Okay, so as I said earlier, you can see that things like ALU source and ALU op are no longer needed because I only need them in the EX stage, and once I use them, I don't need to transfer them over to the MEM stage. Okay, and now for the memory stage, what do I need to do? I need to read the data from the data memory. Okay, and of course, once the data is available, I have this, but I also have the ALU result, okay, that I also need to transfer over, okay, together with some of the control signals over here, and I also have the destination register. Okay, so the memory write back stage have this information here. Okay, again, as I mentioned, some of the access that you see here means that there is actual data, it's just that it's not being used. So for example, this ALU result, okay, it's not being used because in this case, a load word instruction, I'm only interested in the content in the memory. Okay, so I'm not interested in the actual ALU result, which is actually giving me the address. Okay, and this destination register number 24, okay, which is your RT bits, gets followed through all the way. Okay, so that when I complete the instruction, the data is sent back, okay, to be written back here. At the same time, the destination register is also being sent back here. Okay, so when I complete the last cycle, the the write back cycle, I will be able to write back the correct data to the correct register. Okay, so that is your first instruction. For the second instruction, again, very similar. So I will just go through briefly the whole idea. The first stage is, of course, your entire MIPS encoding here. Okay, and once you do your MIPS encoding, okay, again, this is your single cycle analysis. So I will just quickly go through. Okay, so in this case, you have your register 1 and register 3 over here. Okay, so let me just erase this. Okay, because this is actually register 1 information. Okay, this is register 3, and what comes out is your RD1 and RD2. That means your register 1 data and your register 3 data. Okay, and this gets channeled here, and what you're interested in here is actually the E0. Okay, together with the branch for you to make a decision. Okay, and of course, if you recall from your tutorial 4, uh, I will still be generating some ALU result because a BEQ is actually a subtraction, so I'll still be generating something. Okay, and I will also be channeling that over here. Okay, so two information will come to this register, to this multiplexer, but it doesn't matter what goes through, because eventually your register write will be a 0. Okay, and mem write and mem read are also 0, so nothing affects the memory, and nothing will eventually be returned back to the registers over here. Okay, so this is your single cycle analysis. Okay, so coming to our pipeline processor, after we fetch the instruction, we decode it. So once we decode it, we get the control signal. So these are all the control signal that we just saw. Okay, again the PC plus 4, and this R data 1, R data 2 is the data in register 1 and data in register 3. Okay, in this case, your RT RD bits, which is actually for your write back, don't actually have any significance here. This immediate value, of course, is used for your branch target address calculation. Okay, so this immediate value here that you pass through will eventually be used for your branch target address, which will be generated at the end of the EX stage. Okay, so if I look at the EX stage, I will now have a branch target address together with the branch bit that will be set, and I'm interested to know the E0. Okay, so of course, even though it's a branch instruction, I still have to go through the next clock cycle, which is the memory write back cycle, and this does not involve any memory access or does not involve any write back. So you can see that all of these X, and since my register right here is a 0, nothing gets returned back eventually. Okay, so it's important to note your memory write and memory read are 0, and these multiplexers MTOR is X because you don't care what goes back as long as your register write is 0. Okay, so this is how the BEQ instruction would have flowed through. And the last instruction is your subtraction. For subtraction, again, the same thing. This is your MIPS encoding. Okay, and once you do that, okay, so let's look at it from a single cycle perspective. So for a single cycle perspective, okay, what you have is your 20 here, uh, register 20, register 5, and this is your register 25, okay, which will come through here. Okay, so register destination has to be a 1, register write has to be a 1. Okay, so you have two data that comes through here. So ALU source has to be a 0. And this result, we are interested in this aspect of it. So mem to register has to be a 0. And then you write back. Okay, so I'm just again quickly going through. The more detailed explanation is in the tutorial 4 video. Now, this second stage, okay, basically as what you have seen, you are taking data from the register file, the control unit, and as well as sign extension. Okay, so you have all of this information from your control unit. You have your PC plus 4, you have your two registers, RS, RT, and your destination register is your 25. Okay, so in this case, there is no immediate value, there is no RT as a destination. So all of these are X. And in the ALU, you do the ALU op, you get the ALU result. Okay. At the same time, you have a target address, but it's not being used. So of course here, for example, branch target we put as an X because it's not being used. Okay, and you have an ALU result, which is a subtraction operation. Okay, and of course the control signals like ALU, source, ALU, op are already used in the EX stage. So I do not need to use them again in the MEM stage. So that is why I don't need to keep them. Okay, and of course your destination register number 25 still gets carried through. Okay, and in the last stage, a mem to write back. Okay, this does not involve any memory access, so your memory read and memory write are both 0. Okay, your memory to register here is a 0, and register write is a 1. Your destination register is 25. Okay, so the memory result here is X because even though you provide ALU result as the memory address, your memory and mem write are 0. So there is no effective memory result that has any impact for us. Okay, so there is some data there, but we just put it at X because we're not looking at it. We are only interested in this, the ALU result, which is channeled back to register 25. Okay, so what I've tried to show you is how these three instructions would execute through the pipeline processor. And what we will see is the execution flow is actually exactly the same. It's exactly the same as your single cycle processor. Okay, nothing has changed. Okay, the only thing is now we have added latches at each stage so that when it goes from one stage to the next stage, information that is needed for the subsequent stages are still carried on and safe. Okay, but the flow, the multiplexers, the control, everything is the same. Okay, everything is the same. So it's just that these latches help us to hold on to information as you go from one stage to the next stage. Okay, so if the three instructions that we just saw are executed in sequence, what will change? So first thing that we will change is the instruction address. Okay, because it actually in sequence means the addresses will be 4 bytes away. Okay, so if I were to load the first instruction, okay, that will go to the IFID stage. And subsequently, when the second instruction comes in, so this is actually from your instruction 1, and this is your instruction 2. Okay, so instruction 1 goes to the IDEX stage, and instruction 2 is in the fetch and decode stage. And subsequently, when I go to the third instruction, okay, so this is your first load word instruction, this is your BEQ instruction, and this is your subtract instruction. Okay, so you can see that it flows through stage by stage, okay, until it fills up the entire pipeline. Okay, of course, this is very ideal, okay, but of course, we have a very important thing to consider, which are your hazards. Okay, so in the next few videos, we're going to talk about the other questions in tutorial 5 and understand how we can deal with hazards in the pipeline processor. Okay, thank you.